Hey everyone, welcome back to my YouTube channel. Today I'm going to share my learning note about how to convert MIDI to Parsons code. So I'm going to demonstrate how to do this using Go programming language. But before that, I think I also need to share about what is Parsons code and how we are going to convert the MIDI to Parsons code. Okay, disclaimer, I'm not an expert in music engineering. I literally just read it like yesterday, so maybe the information here is not 100% correct. So let's begin with the explanations of Parsons code first. So this is the explanations. Parsons code, or Parsons code for melodic contours, is a simple notation used to identify a piece of music through melodic motions, movements of the pitch up and down. So it's some kind of notations of melody captured from the pitch up and down. Okay, so in terms of the notations, the first tone will be asterisk, or like the star symbols like that, and then the following note will be depend on the previous note. If the next note is higher than the previous one, then we will write U as up, so this is indicating that the note is higher than the previous one. D for down if the next note is lower than the previous one, and R or repeat if the note has the same pitch as the previous one. So let's see example here. So I have a sample melody over here. Okay, da 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 da. So the first note is what is that? Asterisk, right? So the first character, the first note is asterisk. The second one, because the pitch is lower than the previous ones, we write D. The third note is the same, so you write R. The next one is higher, so we write up. So tang 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 D, tang tang, up and up, right? So the Parsons code for that melody is asterisk D R U D U U, right? Alright. So now we are going to learn a little bit about MIDI files, and then let's see how we can convert MIDI files to Parsons code. So MIDI stands for Musical Instrument Digital Interface. It's basically a bunch of protocols that instruct a machine, can be computer or synthesizer, to make some particular sounds. Okay, and the instructions is in the form of MIDI events. So these events that will instruct a computer to make sounds. So let's check what is MIDI events. An event, right, consists of two pieces of informations. Okay, so in one MIDI files, it consists of more than one events to produce a sounds, and each event consists of two pieces of information. The first piece is called MIDI Ticks. It basically specifies at what time something should be done. The second piece is MIDI message. It specifies what should be done. Okay, MIDI message specifies what should be done. MIDI Ticks specifies when this message should be done, right? And for MIDI message, it has four types. Okay, so the first type is voice message. It means that messages that directly affect the produced sound. So I highlight this because this is what we are interested in. The second type is system common messages, system real-time messages, and meta messages. Okay, now let's take a look about MIDI not on message. So MIDI not on message is basically a part of the voice messages, right? You can think that voice messages type has a subtype, and one of them is not on messages. Okay, so if we receive an event and it's a voice messages and it is a not on messages, this type of event indicates a note should be played and should stop sounding. Okay, so for this particular type, it has two parameters. The first one is the note key, like C, D, F, right? The note key in the musical, and a channel. So I'll explain about channel later. The second parameter is the velocity of the notes. So it indicates the strength or volume of the note. Yeah, how hard, how strong the sound is. Okay, so 0 means no sound. Okay, so let's check event example. So this is the event examples, right? It's a hex codes. Yeah, it's basically collection of bytes. So the first part, or x50, is the hex code. If we convert it to decimal, it becomes 80. Okay, so this event, this part of the event, means that this particular event should occur 80 MIDI ticks after the previous event. So when this event should be executed, basically, right? So this event should be executed after 80 MIDI ticks from the previous event. So MIDI ticks here I'm not going to explain, because for this particular learning we are not going to touch that. But if you're interested to check it out, I'll share it in the descriptions. So this is the MIDI ticks. The second part, which has three parts, right? This is MIDI messages. Okay, so the first part of MIDI messages, or X90, this is the status byte of not on messages. Okay, so if we receive OX90, it means that these messages is having a type of not on messages. Okay, which will be played on channel 0. Okay, I will explain about that after this slide. Because this is not on messages, we can assume that after it will have two more hex codes. The first one is OX26. If we convert it to decimal, it is 38. This is indicate the note to be played. In this case, 38 is D in lower octave. So we are going to see there is a table basically that we can reference this number into the key. And then the last part is 60 in decimal. This is the velocity, right? The velocity is arranged between 0 and 127. Okay, so this is the example of event. So this is the table of key by number. So 38 from the previous example is D in a lower octave, right? This is lower octave, this is like the middle, and then this is the higher octave. Okay, now let's explain about MIDI channels. MIDI channels is a communication pathway within the MIDI protocols that allow devices to address and differentiate between multiple instruments or sound sources. Okay, if you think that there is a software to make a MIDI sound, they can differentiate sound sources from channels. From the previous example, we know that OX90 is status byte of note on message which we played on channel 0. So how we know this is channel 0? Because basically, right, for note on messages, the hex will be arranged, the status byte will be arranged from OX90 to OX9F. So if we write it down from 0 to F, it will have 16 channels. So starting from 0, channel 1 until channel 15. So MIDI can transmit informations within maximum 16 channels. Okay. And then channels have relation with tracks. So I need to explain about tracks as well. So tracks basically is a sequence of MIDI events, usually represents musical data like notes, control, changes, or other messages. Tracks commonly used for arranging and recording music. And tracks often have associated attributes such as instrument assignments, volume levels, and etc. etc. Okay, so I'll explain the relations between track and channel with illustrations. So let's say I want to make a MIDI sound using a software. So I plug in my keyboard, right? And then I play a bunch of sequence of notes, right? And then I plug in to channel 4, for example, for my keyboard. So this is the first track. Because I play a bunch of notes, that will be translated into several events, right? And let's say I have another instrument, drum pad, for example. I plug in into channel 6 and I play a sequence of drum music, and then it will translate it into series of events. So in the software, I can get the sounds of my keyboard from channel 4, and then I can get the sounds of my drum pad from channel 6. So I can play them independently if I want. I can edit them independently. And then technically,
We can also add more than one instruments into a single channels if we want, right? Technically, it is also possible. So at this point, we know how MIDI works. So let's try to answer how to convert MIDI to Parsons codes. So first, we need to able to capture MIDI messages, right? The events has two parts, right? MIDI ticks and messages. We need to capture the MIDI messages for each track. And then for each track, we try to capture the note with type not on. And having velocity greater than 0, right? And then we compute the Parsons code by the following logic as usual. First note become asterisk, and second one, if the following note is higher, then we write U. If the following note is lower, then we write D. Else, instead, if the note is on the same pitch, we write R. Okay, so this is the references. I'm going to share it also in the video descriptions. So after this, I'm going to show you how to convert MIDI files to Parsons code using Go programming language.
Okay, so let's start the demo. So for extracting the messages, we are going to use existing code, existing library called gitlab.com/gomidi/midi/v2. Right, this is an existing package that we can use to extract those messages, right? So let's get started. Where is that? All right, so I already have a MIDI file over here. Let me play it for you. That's in the desktop. Okay, that's the MIDI file, exactly the same with the one that I use in the presentations, right? Let's initialize go mode init. Let's call it a MIDI Parsons, right? And then let's get the dependency that we are going to use. Okay, gitlab.com/gomidi midi2. Okay, okay, take some times. Okay, there you go. Now let's create main file. Okay, so let's create package main file, right? So I hope you're able to see this. Right, submit again. Right, so let's import the dependency. Right, the package that we are going to use is smf. This is the sub package. Inside that there is a read file functions, right? It returns smf struct and an error, so let's pass the path over here. MIDI example, MIDI dash sample dash 100.midi. It return SM abstract and error. So if error is not nil, let's print something over here. Right, so slug.error say could not read MIDI file, read file. Right, the error is this one. Right, so let me try this first, if it works or not. Okay, go run game.go. Yeah, it works. Error could not read file. Error is open MIDI example. Blah 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 blah. Right, cool. So we get the SM abstract. Inside that struct, we have access to tracks which contain MIDI events. So we have we are going to use 4 0 yeah, right, then until the length of the track, no, I think let's use for each. So we have track, range of tracks. So track is a bunch of events, right? So we have event range track, right? Let me double check again. Yeah, event. So this is the event, and each event has messages. So let's capture that. Message is events dot message. Okay, now event dot message has a method get not on, returns true if and only if the message is a not on message type. It also extracts the data of the given arguments, which is we are going to have channel, key, and velocity. Nice. So let's use that. Get, what's that? Get not on, right? Channel, key, and velocity. So let's prepare that. Channel, key, and velocity. It's unsigned integer 8. Let's pass it over here. Channel, key, and velocity. So if the message is type get not on, and we are also need to check the velocity just to ensure it's not silent, right? It has a volume of it. Then we want to collect the key, so for this track, right? So therefore let's create that. Let's call it nodes. It's a list of unsigned integer 8 with the length, no, with the capacity of track, right? So nodes append key, right? So we have nodes for each track, so we need to convert it to Parsons code, right? So let's say we have Parsons code, convert Parsons, and nodes, right? We don't have this, we'll create that later. So if Parsons code is not empty string, then we are going to print line, no, printf, okay, track number, and then the Parsons code, and then the wait, oops, what is that, and then new line. Okay, so track number I, and then +1, and then the Parsons code. So let's create the functions. Parsons code. It receives a list of unsigned integer, return string. Okay. Right. So if length of the nodes is empty, just return empty string. I'm going to use a strings builder. Okay, so for the first node, let's write the star characters. Where is that? There you go. Okay, for the next one, let's use for loop. Nodes plus. So let's use switch case. So case, if current node higher than previous one, then let's write string up u, right? If lower, let's write d as down, and default will be repeat. So r, oops, r. Now return b dot right. No, b dot string. There you go. Right. I think that's it. So let's run dru du. Let's compare with the slide quickly. Right. So dru du. Tang 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 tang. Right. So program is correct. Yeah, that's all that I want to share with you. I hope you enjoyed